Good evening. My name is Thomas Tucker. I'm an engineer within my organization's IPNOC, and this is going to be an introduction to the services architecture on the Nokia service router platform. And we're going to assume that you're familiar with dynamic routing and label distribution within an IP network, as well as VLANs and basic switching. So this is the services model uh, that SROS uses. And it seems like there's a lot going on, but once you become familiar with the definitions and familiar with how uh, each part is sort of layered on top of the other, understanding and deploying services becomes pretty simple. So let's start with our subscriber, which isn't shown. That's going to be our end user. I wouldn't refer to a subscriber as a customer because customer has a different meaning in the context of the service router platform. We have our SAP, our service access point, which like the subscriber isn't shown, but it's the interface that connects the subscriber to the service provider. So this would be like our sub interface on a Cisco, or if we had a VLAN dedicated to a customer on Junos, this would be our unit number. And we have the customer ID or customer, and this is a unique value used to group services together. We have the service ID, which is a unique value used to identify the service. And our service distribution point, or SDP, this is a logical representation of the transport tunnel emulating a direct connection to a far-end PE router. So like we discussed in our previous video about targeted LDP allowing labels to be signaled between non-directly connected peers. Well, this is an example of a targeted LDP session, our service distribution point. Next, we have the transport tunnel, and this is the label switched path that's used to transport the service data, and its labels are signaled by link LDP. And we have our service tunnel, and this is represented by service labels, and its labels are signaled by targeted LDP, or in the case of a layer 3 VPN, BGP labeled unicast, or you can also refer to it as multi-protocol BGP. And last, there's demultiplex, which is the act of decapsulating data arriving at the egress PE router. It's typically a POP operation of MPLS. So when we say demultiplex, we usually mean that this MPLS packet with a label stack arrives at the egress provider edge router. That provider edge router demultiplexes that packet by removing the transport label, exposing the service label. It then demultiplexes that service label or pops that service label off, then multiplexes the VLAN tag if appropriate, or if applicable, I should say, as well as a frame check sequence for egressing that datagram onto the customer. Now, I probably should have touched on this in the LDP video, but just so that we're familiar with it, let's go over the types of transport. First, we have GRE, or generic routing encapsulation. This is a method other than MPLS to channel packets across an IP network. So a few important things about GRE tunnels. Packets are routed through the tunnel based on source and destination IP. So based on the information in our delivery header, that's how we get from the ingress label edge router to our egress label edge router. The delivery header source IP field contains the ingress LER, and its destination IP field contains the egress LER. And the protocol's ether type or protocol type field defines the type of packet. In our case, hex value 0x8847 translates to this being an MPLS unicast packet. And this blue header here, this is our service packet or customer payload. So this would be the frame that, the customer frame that ingresses the service provider. Once it ingresses that PE router, and if in the case we're using GRE to tunnel this from our ingress LER to our egress LER, it'll be encapsulated with all these different headers. And of course, the frame check sequence will be recalculated. We're most probably not going to use GRE. Well, really, we're not going to use GRE. This is more or less reserved for legacy equipment or legacy operating systems that simply don't understand MPLS. But for the sake of example, maybe when we get around to configuring our ePipe, we'll use one ePipe delivered by GRE and the other ePipe delivered by MPLS just for the sake of seeing a GRE packet in action. But from here on out, our method of transport is going to be MPLS. And like we discussed in our previous video, MPLS, or multi-protocol label switching, is a service that allows data to be forwarded based on labels rather than routed based on IP headers. So when the same customer payload or service packet ingresses our ingress or our ILER, instead of being encapsulated in a GRE header, it's simply labeled. So this service label, of course, is going to come from our service, but the act of getting this particular packet with this particular service label from our ingress LER to our egress LER is going to take place via GRE, or can take place via GRE. And that's when we'll have these additional headers, our delivery header for our source and destination label edge router, and our GRE header with the ether type. But in the case of MPLS, that same customer payload or service packet belonging to that same service simply has a transport label pushed onto it. So going back, we talked about demultiplexing as decapsulating data arriving at the egress PE router. Well, multiplexing would be encapsulating data arriving at the ingress PE router. So first, the service label is pushed onto it, and then the transport label is pushed on top of that service label. Now, these are the types of services, and I really encourage you to read through the RFCs. And in the case of these layer 2 VPNs, not just RFC 4664, but also 4665 as well. Both contain extremely useful information. But each of the RFCs that define the type of service that we're going to be delivering, in order to really gain an understanding, and not just with these services or these models, but protocols in general, in order to really gain an understanding, you have to be familiar with the protocol at the RFC level, like at the bit level, so to speak. Simply learning how to do it on a particular platform isn't going to be of any use, because of course things like interoperation exists. So even if you know these, how to deploy these services soup to nuts on a Cisco or soup to nuts on a Juniper device, that won't help you much without a deep understanding of how the protocols operate. Because at the most basic level, these different vendors are just, the difference between the vendors or the operating systems is just semantics. The protocols all operate and behave exactly the same. So again, I encourage you to learn these protocols on the RFC level, because the terminology that we're going to be using as well is lifted directly from these RFCs. So the first two are layer 2 VPN services, and the last two are layer 3 VPN services. First, we have a VPWS, or Virtual Private Wire Service. It's also called a VLL, or Virtual Lease Line. And this is a virtual point-to-point service that emulates a private connection. So in our example, we have an e-pipe, and this emulates a point-to-point Ethernet service. Of course, it supports all layer 2 technologies. Next, we have VPLS, or Virtual Private LAN Service. This is an Ethernet service that connects multiple sites in a single switched domain over an IP MPLS backbone. A real good manager I had, Bradley Mitchell, during my tenure at CenturyLink. He called this a LAN over a WAN, which describes it to the T. But when I was learning about VPLS, that one phrase really simplified things. A LAN over a WAN. So with a VPLS, the service provider appears as a virtual switch to the subscriber. I didn't state this explicitly, but in the case of an e-pipe, the service provider just appears as a virtual wire or a virtual circuit to the subscriber. And in the case of a VPLS, the service provider appears as a virtual switch to the subscriber. So all of the subscriber sites are inside of their own broadcast domain. And for layer 3 VPNs, we have a VPRN, or Virtual Private Routed Network. And this provides a multi-point routed service to the subscriber over an IP MPLS backbone. The service provider appears as a virtual router to the subscriber. So in the case of a VPRN, each customer site can have its own network, but each network will be reachable through the service provider. So it's as though the service provider is acting as a virtual router to the subscriber, allowing the subscriber to segment and interconnect their broadcast domains. And last, we have an IES, or Internet Enhanced Service. And this is a layer 3 interface provided to the subscriber, treated as a service and configured as a SAP. And this supports QoS accounting and filtering. And in the most simplest of terms, an IES is a way to provide core-facing capabilities to a customer-facing interface. Because normally things like QoS accounting, filtering, those are all done on core-facing interfaces. But this allows you to perform all those functions on a customer-facing interface. So for example, if we had a triple play service, it's real popular to deploy IES as a way of controlling your DSL subscribers. So moving on to our first service, which is going to be a virtual private wire service, or an e-pipe. There's a lot going on here, but we're going to step through all of it. So we have a customer A Incorporated. The customer has two sites, R1, which is located in Los Angeles, and R2, which is located in New York. And the customer wants nothing more than for the service provider to configure their service in such a way that whenever these sites are connected to the service provider, logically, these routers would act as though they were directly connected. So they're asking the service provider to provide a virtual circuit between their sites. So first we're going to just walk through the traffic progression here, and then we'll get to the spoke SDP and whatnot. But so let's say on the customer's site in Los Angeles, they have the IP address 10.0.0.0/31, and their site in New York is on the other end of that point-to-point network with the .1 address. And let's just say this were an ICMP packet, just a ping from R1 to R2. First, this frame would ingress the service provider through this particular service access point, 115:10, with 10 being our VLAN, or it's also called a service delimiter. I'm sorry, 1 second. All right, sorry about that. So just starting from square zero here, we've got R1 and R2, a customer with or a subscriber with sites in different locations, and they'd like the service provider to emulate a virtual circuit so that these two sites would logically think that they were directly connected. So traffic from R1 ingresses the provider edge N1. And again, going back to our LDP video, we're going to assume that traffic is flowing from R1 to R2 in this particular example. So we've got our packet from R1, and it's got our source MAC address of our interface and our destination MAC address of our directly connected switch. But more importantly, it's got our VLAN tag of 10 and our source and destination IPs. So the first thing that happens when this frame ingresses the provider edge on this particular SAP 115:10 is it's demultiplexed. So the VLAN tag and the frame check sequence are removed from the subscriber frame before the frame is multiplexed. So the first thing that happens, the 802.1Q tag and the frame check sequence are both ripped out. And of course, the frame check sequence is recalculated before egressing, but so after that VLAN tag is removed, the frame is then multiplexed. So based on the ingress SAP, a service label denoting which service this frame belongs to is pushed onto the subscriber frame. So in our example, this ePipe is service ID 87, and our service label that targeted LDP generated just happened to be 87 as well. So that service label is pushed onto the subscriber frame. And based on the service distribution point's far end, a transport label is pushed on top of the service label, creating a label stack for the far end's forwarding equivalence class. So based on our targeted LDP session, that's going to describe or dictate our transport label. So in our example, our targeted LDP session is running from N1 to N6. So N1's label in its label forwarding information base for N6's forwarding equivalence class of its system address, which was 6.6.6.6/32, is the egress label 101 with a push operation. So we have our label stack. And of course, after that, the frame check sequence is calculated and the frame is egressed uh, based on this label's egress interface. All right, so let's say that just for the sake of example, the same datagram ingressed into and into's LFIB, any datagrams arriving with an ingress label of 101 have an egress label of 202 attached to them, along with a swap operation. So when N2 ingresses this MPLS packet with the transport label of 101, it swaps the 101 for 202 before egressing this packet out the interface destined for the next hop in our label switched path, which in our case, of course, would be router 3. Router 3 does the same. Oh, let me read this description. Service ID 87's datagram is label switched across the service provider's network based on the transport label. At each label switch router along the label switch path, the transport label is swapped before the datagram is egressed. The service label of 87 remains untouched. So all that our label switch routers are doing is swapping our transport label. 101 for 202, 202 for 303, 303 for 404, 404 for 505, and then router N5 swaps 505 for 606 and egresses that MPLS packet to N6. So the first thing that happens when this MPLS packet with a transport label of 606 arrives at router N6, let me just read the description. When the subscriber frame ingresses N6, its transport label, now 606, is popped, revealing the service label of 87. The frame is further demultiplexed by stripping the service label of 87 before being multiplexed. So when this frame arrives, it's got a transport label of 606 and of course a service label of 87. The 606 gets popped off. Router N6 examines the service label of 87, pops it off, and does the following. The subscriber frame is multiplexed with the service's VLAN tag. Its FCS or frame check sequence is recalculated, and it's egressed out the appropriate SAP toward the destination, which is R2. So once N6 demultiplexes this subscriber frame, and by demultiplexing, we mean not only popping the transport label, but also popping the service label, it then multiplexes, or can I say remultiplexes or multiplexes that subscriber frame. So depending on that service label, it's going to know what VLAN tag or 802.1q tag to push. I shouldn't say push, but it's going to know which tag to tag this frame with. And in our case, it's a VLAN of 10 belonging to service ID 87. And after that subscriber frame is tagged, the frame check sequence is recalculated, and then that frame is egressed toward the destination, which ultimately is R2. So the main thing to take away from this is that when customer data arrives at the ingress label edge router, the ingress label edge router pushes a service label onto the subscriber frame, then pushes a transport label, creating our label stack, before egressing the subscriber frame, now encapsulated in our label stack as an MPLS packet. And at this point, the packet is no longer being routed. It's being switched based on the source and destination MAC. And of course, label switched based on our transport label. And during its transit from the ingress label edge router to the egress label edge router, the only data that's changing in this frame, other than the obvious being our source and destination MAC, as well as our frame check sequence, the only information changing in this frame is going to be our transport label. And of course, our LSRs, they're only responsible for swapping labels along a given label switch path. And when this MPLS packet arrives at the egress label edge router, the transport label is popped, revealing the service label. The service label is then popped so that the egress label edge router knows what VLAN tag, if it's supposed to be tagged, and what egress, what SAP to egress this packet out of. So when information enters the service provider network, it's assigned a label stack, and it's then label switched through the service provider network and demultiplexed at the egress label edge router. So this is what our virtual private wire service, or our ePipe, would look like from the customer perspective or the subscriber perspective. They have R1, which is their subscriber site in Los Angeles with the address ending .0. And then they have R2, which is their site in New York with the address ending .1. And in the middle, we have the service provider IP MPLS core, which is emulating our virtual circuit. So in each of our subscribers, each of the ARP tables on these routers, we'll have one local route. In the case, it will be on R1, it will be this .0/32. I'm sorry, .0/31, and then we'll have our connected route, which will be the .0/32. And in the case of R2's routing table, we'll have the .1 as a local route, .1/32 as a local route, and .0/31 as our connected route. So the only networks that these routers are going to be familiar with is this /31 network. They aren't going to be aware of the service provider in between connecting their site in Los Angeles to their site in New York. From these two routers' perspectives, they're in the same rack with a Cat5 cable running between them. So now let's move on to VPLS, or Virtual Private LAN Service. And like we said before, this is a way to provide the customer with their own broadcast domain. So an easy way to look at this is just a fully meshed network of ePipes, if that helps. But of course, there's a lot more to it. The first being that in a VPLS, the provider edge routers are MAC aware, which means that they learn the MAC addresses of the customer equipment. So in our case, R1's MAC address is learned by N1, R2's MAC address is learned by N6, and R3's MAC address is learned by N7. But our SDPs work the same way, in that they allow labels to be signaled between our provider edge routers that allow our pseudo wires to carry the service. But unlike our ePipe, and I didn't speak on the Spoke SDP, but this is our pseudo wire. Spoke SDP, in particular 87:87871, with 87871 being our virtual circuit ID. This configuration of the spoke SDP on each side is what establishes our pseudo wire. And once our pseudo wire is established, our service labels are then signaled. So it works the same way in a VPLS, except instead of having spokes, we've configured meshes or mesh SDPs. And VPLS is a very complex service, and there are a million ways to build a VPLS. But just for the sake of simplicity, we're going with the vanilla VPLS, which is just a full mesh of service distribution points between our provider edge routers. So when we take a look at R1, we see that R1's MAC address, which is A.0001, it's associated with this particular IP address, 172.16.0.1/24. And the important thing to make note of is that all of these customer sites are going to be on the same network or within the same broadcast domain. And on R2, in R2's case, its address is going to be .2 in that /24 network, and its MAC address is all B's.0001. And in R3's case, its address is going to end in .3 on that /24 network, and its MAC address is going to be all C's.0001. Now, the first thing that occurs is router N1, or I should say the directly connected PE router, learns the MAC address of that customer site that's attached to it. And the mapping for that particular customer MAC address is going to be local or designated as local inside of the VPLS's forwarding database, because this provider edge router understands that in order to, that this MAC address is directly connected. Traffic doesn't have to travel through a service distribution point from N1 in order to reach R1. So inside of the VPLS services forwarding database, our mapping for R1, or R1's particular interface, which is all A's.0001, is going to be local. And these MAC addresses that are all zeros, these are the switches, and they aren't represented on this picture, but there's a switch that sits between the router or our subscriber router and our provider edge router. So this MAC address you're seeing is the switch interface that's facing our provider edge router. So our provider edge router learns the MAC address not only for the switch that's facing it and connected to R1, but it also learns the MAC address for our interface that's part of the VPLS. And that process happens at each provider edge for each router. N6's forwarding database for VPLS 6.5, it knows that these MAC addresses that begin with B are local or directly connected. And in N7's forwarding database, it knows that these MAC addresses that begin with C are directly connected as well. Now, once we establish our service distribution points in a full mesh, then the provider edge routers begin to share this MAC address information, or they flood this MAC address information to the other provider edge router that's at the far end of our service distribution point. So, and of course, those mappings are saved in the VPLS's forwarding database as well. So let's look at SDP 102 that runs between N1 and N6. N1 has learned that in order to get to the devices whose MAC addresses begin with B, uh, it's going to have to use this particular service distribution point. So it learned these MAC addresses through this SDP. So if N1 were ever to ingress a particular frame whose service was tied to this particular device attached to this PE router, it would know that in order to reach the far end, or N6, it would have to forward this traffic out SDP 102. And the :65, you could think of it as a VCID, but in the case of VPLS, that's always going to be the VPLS service ID. So in the case of SDP 102, that pseudo wire is SDP 102:65. In the case of SDP 100, that pseudo wire is SDP 100:65. So we can see that each provider edge router eventually learns the MAC addresses of each other provider edge router and also maps those MAC addresses in their forwarding database. So N1 knows that frames destined for a device whose MAC address begins with C gets forwarded out SDP 100. And of course, N7's mapping is that these MAC addresses that begin with C are local, so it egresses it out the SAP 115:20. So again, from the service provider's perspective, in order to maintain or in order to deploy a VPLS, each provider edge router has to maintain the MAC address table, or I shouldn't call it a MAC address table. Each provider edge router has to maintain a forwarding database for the VPLS. Now, this can be dangerous at times because you do reach limits as far as the available space of wherever that forwarding database is stored. Things like you might run into a situation like MAC address explosion, where these provider edge routers are just simply overwhelmed with learning and flooding MAC addresses, and it's enough to crash a router. But looking at the ARP tables for our routers here, we can see that in our ARP table for R1, and this is of course after we ping router 2 and ping router 3, we can see that in our ARP table we do have the valid IPv4 address for those devices, as well as the valid MAC address for those devices. So the data in these subscriber frames or customer payloads was preserved. And from the customer's perspective, this is what our VPLS, and again, there are a million ways to deploy VPLS, but for the sake of simplicity, we've just deployed it in a full mesh architecture. So in the middle, we have our service provider and their IP MPLS core, which is going to emulate a virtual switch. In R1, we have our subscriber site in Los Angeles. He's part of this /24 network with the address .1. R2, we have our subscriber site in New York. He's part of this same /24 network with the address .2. And R3, we have our subscriber site in Dallas. And again, they're part of the same /24 network, just addressed .3. So from the subscriber perspective, or from the perspective of these devices, logically, they're under the impression that they're all sitting in the same rack, connected to one switch. So all these sites are within a single broadcast domain, and that broadcast domain being the /24 network. All right, and this is the one that everyone's probably the most familiar with, which is your VPRN, or Virtual Private Routed Network, or your Layer 3 VPN. This is sort of like the bread and butter of IP service deployment. But one thing I want to also say is that in the case of our Layer 2 VPNs, our Virtual Private Wire Service, and our Virtual Private LAN service, our service distribution points, in the case of our ePipe SDP 87, in the case of our VPLS, SDPs 100, 101, and 102, these are all targeted LDP sessions. So those labels are being signaled via targeted LDP sessions. Now, when we get to Layer 3 VPNs, instead of those labels being signaled through targeted LDP sessions, they're going to be signaled, or I can't really even say signal, but they're going to be exchanged through BGP labeled unicast or multi-protocol BGP sessions. So in the case of our VPLS, we had a full mesh of service distribution points, which were just targeted LDP sessions. So N1 had a targeted LDP session to N6 and N6 to N1. N1 had a targeted LDP session to N7 and N7 to N1. N7 had a targeted LDP session to N6 and N6 to N7. It's the same way when we deploy our Layer 3 VPN. N1 is going to have a BGP labeled unicast or multi-protocol BGP session or neighborship or peering to N6 and N6 to N1. N1 is going to have a BGP peering to N7 and N7 to N1. And N7 is going to have a multi-protocol BGP peering to N6. And of course, N6 back to N7. But we aren't using regular BGP, hence the extension labeled unicast or the preface MP or multi-protocol BGP. Instead, we're using a specific flavor or an address family within BGP called the VPN v4 or VPN IPv4 address family. And that's what's going to allow our VPNs or our VPN routes to be exchanged. So I don't want you to have the impression that these are going to be regular iBGP or eBGP peerings between our provider edges. We're running a modified or an enhanced version of BGP between our provider edge routers. And in this particular enhanced version of BGP, we're just using the VPN address family. In particular, VPN for IPv4 routes. So in the case of our VPLS and our VPWS, these service labels are being signaled by targeted LDP via this pseudo wire. So once we establish the pseudo wire, then the service labels are generated. And once the service labels are generated, they're signaled through this targeted LDP tunnel. In the case of our Layer 3 VPN, instead of using a pseudo wire to signal these labels, we're going to use what's called a route target And once we have a route target configured, then our service label is going to be generated. And once our service label is generated, it's going to be carried through this BGP labeled unicast or multi-protocol BGP peering in an update message via an extended community. So our route target is also called an extended community, and that's what's going to denote which particular VRF that a customer's route belongs to. And there are also other concepts like route distinguishers and whatnot, but we'll cover all of that during the presentation on deploying VPRN services. But the main thing to take away from this slide is that make sure to take note of the routing table on our provider edge routers. We're able to share address space regardless of the particular subscriber. So subscribers A, B, and C, all of their address space is shared on the provider edge router. So for example, in this particular VRF 1122, our customer router or our customer site has the address 192.168.1.1/31, and it's peered via eBGP with our provider edge router. And our provider edge router, of course, is going to be the .0 of that point-to-point network. And that process is repeated for all of the subscribers connected to N1. They all have the same address space. The same on N6. Everyone's using 192.168.2.0/31. On N1, everyone's using 192.168.1.0/31. And on N7, everyone's using 192.168.3.0/31. But again, the main thing being that each VPRN essentially segments the router into a router that's separate from the global context. So by creating a VPRN, you in essence create a virtual router for this particular customer. So from the router's perspective and from the subscriber's perspective, it's only them in play. The provider edge router has no concept of other customer VPRNs or routes within other customer VPRNs. Again, that control plane data is kept completely separate, completely segregated. So you can have all of the subscribers that are terminated on a particular provider edge router share the same address space. And as long as we give them unique route distinguishers, then the provider edge router will be able to tell them apart. And as long as we have a valid route target, then an extended community or a service label will be generated and shared for that particular subscriber's VPRN. So let's go, we're going to look at customer C, and I'm going to go back, and only because C has sites terminated on each provider edge router. So that's why we're focusing on customer C. They have a site terminated on N1, on N6, and N7. So from the subscriber's perspective, the service provider, in the case of a VPRN, is acting as a virtual router. So in the case of a VPWS, the service provider emulated just a single virtual circuit. In the case of a VPLS, the service provider emulated a single broadcast domain. Well, in the case of a VPRN, the service provider is going to emulate a virtual router to segment and interconnect the customer's broadcast domains. So on R1, we've got a dummy network, 151.42.1.0/24. That's the subscribers network in Los Angeles. And the subscriber also has another network in Dallas, 151.42.3.0/24. And their network in New York is 151.42.1.0/24. It should actually be 42.2. If I don't change it now, I'll forget. All right. So the point being that these are completely separate broadcast domains. 42.1/42.1.0/24, 42.2.0/24, and 42.3.0/24. Completely separate broadcast domains. However, from the service provider's perspective, these broadcast domains, we'll call them switches. These switches will think that they were all directly connected to a router in the same site or in the same colo. So since they're connected, all three of these networks are connected to this virtual router, traffic can be routed between those broadcast domains. So traffic sourced from one broadcast domain, we'll say the 42.1 network, can reach New York's broadcast domain, which is the 42.2 network. And of course, traffic from New York's broadcast domain, the 42.2 network, can reach Dallas's broadcast domain, which is the 42.3 network. So again, the service provider just emulates a virtual router that allows the subscriber to interconnect their broadcast domains as they see fit. And the last service we have is our Internet Enhanced service. And there's not a lot to this one, but there's a ton of things you can do with it. Earlier we touched on how some service providers they deployed their digital subscriber line or their broadband services as an IES. That way they can provide blanket QoS, blanket accounting, blanket filtering for their subscribers. But you can also deploy an IES in this fashion as well, which is just giving a particular subscriber access to the service provider's core routing. So through the IES, the service provider can establish an IGP adjacency and freely exchange routes with the customer site. So in our example, our customer router R1 has an OSPF adjacency with the service provider, and its provider edge is N1. So here's our local network, 209.43.1.0/31, with of course our CPE being address .1 and our service provider being address .0. Well, that service provider, that service, that IES service, has an OSPF adjacency that's running within it. That's allowing the CPE or R1 to exchange routes with the PE or N1. So looking in R1's routing table, we can see that we have an OSPF route for N1's system address. But getting into the concept of the subscriber having access to the service provider's core routing, we can see that not only do we have a OSPF route for N1's system address, which is the PE router that the subscriber is directly connected to, but we also have external type 2 routes for the other routers within the service provider's routing domain. So our CPE, or our subscriber, or R1, has access or is aware of the service provider's internal routing schema. Why would a customer want this? If I had an IES, I would think that it would allow me to really deploy a lot of reservation protocol, a lot of traffic engineering. I'd be able to build and color label switched paths or MPLS links, knowing exactly how that, knowing exactly how many different hops my links could take, to put it that way. Maybe I notice latency to N3 is higher at the middle of the day than latency to N5. Well, between the hours of 11 a.m. and 3 p.m., I'm going to have a label switched path that sends my high priority traffic through N5. And then, after 5 p.m., I'll have a label switched path that returns traffic so that it transits through N2, So from my perspective, it gives the subscriber quite a bit of control over how their traffic is routed to the internet. But of course, it also gives the service provider quite a bit of control in how that customer traffic is ingressed and how it's egressed. Again, it's capable of QoS accounting and filtering. Yep. Looks like that's it for the day. Our next slide, we are going to get into configuring and deploying services. Our first one, of course, is going to be the virtual private wire service. So we'll just pretty much follow this topology. We'll have R1 and R2 connected through a service provider network, and we will emulate a virtual circuit. And in that one, we'll also build our service distribution point, or our tunnel, I should say. We'll build a GRE tunnel from M1 to N6 and vice versa, just for the sake of being familiar and seeing it, because one day we might run into a GRE tunnel. But again, our main method of delivery, or our main method of transport, is going to be MPLS, or label switching. So thank you for watching the video. Please contact me if you have any suggestions, and I look forward to you joining me for the next one. Thank you.